Okay, yeah, so we're gonna just start. So welcome everyone. Basically, sorry also and apologizing for the a little bit late start here. We had some troubles with a link, but I think this is corrected. At least we have here some participants, which is very great to see. And this is a webinar that we organize essentially out of the RACE CoE project. I will talk a little bit about it in later on. But firstly, I would like to introduce also the speakers of the webinar today and the agenda. So we will talk a little bit about use case foundations in the beginning. So CoE RACE, you will see, is about use cases in different engineering domains, and we make a case for it, why we do so-called fact sheets about them as a kind of input to the interaction room. So why we need the interaction room, why is this a good technique, and so forth as a motivation. Then you see in the second part of the webinar today, we have really the expert here, Matthias Bog, that you already heard before, who will talk about the interaction room approach. And then we will have a small comfort break, which really gives us an opportunity to refill coffee. We may skip this because of the trouble of the link that we had here, but maybe that's a good thing to do still for 5 minutes. And then after this short break, really, we want to go to this HPC systems engineering a bit more in detail. So where is now the HPC elements of it? What could be canvases so far for HPC, and where are new elements needed in research like AI and so on needs to be combined, as you will learn from CoE RACE. The idea is therefore that in the end, we will have still lots of question time, 30 minutes, where we can clarify then also within RACE, but also every one of you who is external from RACE, who would be, having a kind of interesting, question or a discussion item, how that works with interaction rooms. So from the speakers, again, Professor Matthias Bog is teaching software engineering and software development at the University of Iceland, is also the CS department head, so computer science department head, and is really a specialist in this interaction room technique. And for most notably for our CoE RACE and also for EuroCC is of course his industry experience as well. He was with industry before, had then also this technique often with industry. This is quite an important factor. So then also Professor Helmut Neukirchen will enrich his experience working a long time in the deepest series of projects there in the co-design area. So some of you know, hopefully, the deep projects, which is basically now officially ended, but we carry on the ideas in CoE RACE with modular supercomputing, as some of you know. And he is also an expert in software engineering, software testing, and basically also in parallel computing and HPC. I then bring a little bit of perspective how this all fits into EuroHPC. I'm the governing board member of Iceland, and also will pave a little bit the way and show you what Iceland has to offer here, organizing this, but very briefly. So essentially, University of Iceland is organizing this webinar here today. Thankfully, we got the CoE RACE grant, but as all of you also know, the EuroCC project was funded, which gives us all the national competence centers in all the different countries, and we are one of them. And you see how we have bit structures are so-called simulation and data labs. So we see here Matthias Bog and Helmut Neukirchen as part of the software engineering for eScience simulation and data lab. But we have, of course, also many others you essentially see here in this list when you go to the EHPC website. So this is our National Competence Center. Of course, the community building in our country is a little bit young compared maybe to other countries that have already strong computing centers in the past and had already lots of community building exercises. That's why we're also very grateful for the EuroCC project to have this, to really structure and organize our community much better here, what we basically doing constantly now. Then just to mention, we also host the National Supercomputer here as the basically university, but it's really a joint venture funded by the national funding organization RANIS, and this includes the University of Reykjavik. It includes also industry partners, and is really just hosted by us, but really an Icelandic endeavor. I also want to point out we have strategic partners and corporations in terms of HPC since a very long time. DEEP, I was mentioning, that was creating the modular supercomputing architecture, and with this we have been collaborating with Jülich since a very long time. essentially having joined PhDs going back and forth, and we see they're definitively contributing there to co-design in the areas and of different applications, but also in the couple of years to come, hopefully ending up in 2023 somewhere with an exaflop system. But we also see in Iceland, we are part of the LUMI consortium. So this is a system in Finland, but it's also basically a modular supercomputing architecture. It has different partitions inside, and basically there Iceland has also strategic partnerships in this area towards Exascale. It's a pre-Exascale system, but definitively something worth mentioning here. Then at the end, I would like to take just the opportunity to say that we're still searching for really PhD student in the area of remote sensing from the CoE race. That is one of the use cases you will learn about in a couple of minutes from me. But if you're interested or know someone who would be interested to live in Iceland and having also collaboration maybe with the Jülich Supercomputing Center going back and forth, just let me know. And that's really my first welcome talk here for the webinar. I think when there are not crucial critical questions, I would like to proceed to save some time then to my introduction of race, before we then essentially hear a little bit from Matthias spoke about the interaction room. Right, so let's hear about a little bit what CoE race is. I think some of you know, of course, our project because it is partly an internal project meeting here, but also we have now external partners. That I would like to just point out to you a couple of details about CoE race. You see our website is live now. We are kind of 3 months in the project. And essentially, we have now really started to work in the project after the 3 months and have already some initial results I will present. But of course, more information you can really find here on the website. I always provide the link so that you can easily find it. When you then think about the approach, the motivation behind CoE race is really bringing HPC and AI together. So some of you know in the past, we have many traditional HPC users in the area of simulation sciences. So known physical laws, numerical methods. This was basically the modus operandi there. Iterative approaches, stencil methods, Harlow regions. So a lot of MPI, OpenMP. Now, what we have also in the other side now, more recently, are these AI technologies, right? So that means more GPU usage. People of you have probably heard from TensorFlow, PyTorch, DeepSpeed, Horowat, where you also then also scale up with different GPUs. So you don't need to stay on just, let's say, one GPU in some kind of workstation. You really can enter a supercomputer as well. So here's really is the idea to have an intertwined approach to bringing these two worlds together, and this in different use cases. This will not only mean surrogate modeling, also, of course, lots of data sets that needs to be basically dealt with in this project. And those arise essentially from two kinds of use cases. We would have compute-driven use cases, which are really more the simulation sciences, traditional ideas, computational fluid dynamics, for example. And then we have the data-driven use cases where really the idea is on the other side, how do we generate data, where do we generate the data, and how we can analyze it with AI methods, and then complementing it perhaps with some simulations. So when you go to the website, you will see much more details. That's why I don't talk here in this talk too much about it, also that we have enough time for the interaction room. Just you see here a kind of snapshot or screenshot really from the website. You see all the different use cases are described there in detail with some nice graphics that you also can understand them. And of course, this is kind of the foundation in our CoE race really to talk to all of these different representation, models of the data of the experts behind this. And this is part of the lessons learned I want to show you. This is quite a process we have been through, starting directly from the beginning of the process, because you see essentially a wide range of experts from CERN, the LHC, Hadron Collider, up to computational fluid dynamics experts. So we have a very broad range of use cases, which is of course very good, because the idea is then to create something which is also not only tuned for those use cases, but can be used in many other use cases as well. Just briefly, the partners in CoE race, you see here short list, we essentially span whole Europe from one end to the other, from Iceland to Cyprus, which might be the other end essentially here on the European roadmap. And we have also with Safran, with Bull, with Atos and so on. We have, of course, also commercial player on board. I should not forget Partech, of course. So this is an interesting endeavor, an interesting, collaboration we have been in. And some objectives of CoE raise are then essentially developing these AI methods. And of course, we want not just to develop them with one GPU, we want to move towards Exascale, while not neglecting that, of course, the simulation sciences have also the high needs of computing. And that's why we see lots of intertwined use of this with AI and HPC. We have the idea that we really have cutting edge hardware infrastructure. So you have seen probably Jewels as #1 in Europe, but also BSC has systems there. From Barcelona, we have some prototypes also in the quantum computing area in the project. So, and this would be the idea to really try them out with this compute-driven and data-driven use cases. In the end, what we want to achieve is something we call in the moment a unique AI framework. So this is a loaded word, I know. You would say it is not really reinventing the wheel. It would be a library that really consists of open source community tools, of best practices we have already. Things like parallel IO will be considered. And of course, it needs to be and will be well embedded in EuroHPC and PRAISE, and also as part of our national competence centers in EuroCC. Now, when we think more on the industry side, from the results coming out of this project, we really want to do a transfer, from science to industry, think about potential ideas. We're creating a network, a European network that really can have this technology and the knowledge of how to combine HPC and AI really addressed and, let's say, properly organized, especially around Europe, but of course also with our international colleagues. Then we not neglect the fact that, that from the EuroCC and EuroHPC endeavors that we want to engage much more essentially into the business, into industry, involving them in HPC more than we have perhaps done in the past, where more science was driving these activities. So this is something also where we think about sustainability models in the project, and of course connect to other centers of excellence. We know we're not alone. There are a lot of them outside we collaborate with and plan to collaborate in the next couple of years. Now, when I come back to the vision, I told about intertwined HPC simulations and AI. Is that possible? You see here some examples and publications where we have done this already. Not on the Exascale. It was, of course, at that time a UQueen in Jülich, for instance, where we have then used essentially a weather prediction model or meteorological ensembles from 1,000 models, for instance. We did the typical simulation sciences approach. And then on the other hand, we just use a typical particle filter and also a statistical method and also a support vector machine to predict which of those exam ensembles will be not very good, right? So we kind of stopped them early and created new ensembles, which had a much better chance of being successful. So in the end, you had this in situ loop that we also reference a lot, essentially in this project. And of course, here we want to also scale it up really towards Exascale, see how these models now really work and what we can do with them. But you see, essentially, that's possible. And the good question that I often get also as a university teacher, often in events, is, can AI do Exascale, right? So, and use disruptive technologies. Many talk about GPUs and workstations. Here you see an example, for instance, where we use Jewels, Europe's #1 supercomputer right now, with 56 compute nodes. So we used, let's say, four GPUs at the same time on 24 nodes. And with a V100 at that time, nowadays we have even A100s in these systems, and it really works. You can use TensorFlow and Horowot and different AI frameworks across many different GPUs. So that's possible. And here are some links if you want to know more at the EGAS conferences from last year, for instance. But we have also new publications from this year. On the other end of the scale, perhaps very new and disruptive would be our experience now with quantum computing. We work there quite intensively since 2 years of really bridging the old traditional methods from, let's say, the typical supercomputer over to a D-wave quantum annealer. Quantum annealer is quite interesting. And because it can solve optimization problems which are inherent in AI algorithms, in machine learning algorithms. So that's why we have there also quite some nice success. However, we have to say it is a new technology. So the big data is not yet there. We have to sample here and there, but also we see and observe that the D-Wave systems, for example, really are increasing with the number of qubits significantly. So and this is in the RACE project, coming and summarizing a bit now for CoE RACE. Again, the idea how we do this and how the interaction room and the fact sheets and so on will be, let's say, part of the project. We see this really as an iterative, integrated approach. So of course, the hardware infrastructure is as important as the software infrastructure that we know already. And then we should not neglect that, of course, the application requirements from the computer-driven use cases and data-driven use cases are key. We want to do the science or the engineering problem solved. So that is, of course, the number one requirement. We don't want to make AI for fun, right? So in this sense, we really need to listen carefully to the requirements of the domain scientists and this feedback to really integrate it in something we call then the unique AI frameworks that should be fit for Exascale, hopefully in 3 years when the project is ending or transforming, hopefully, to some other sustainable CoE entity. Now, when we think about the details now coming to the process, what we have been done basically the last couple of months, and also what we will continue to do is really supporting these compute and data-driven use cases with a lot of knowledge from AI, which is not only modeling in terms of AI. You see here, we offering as part of this library elements of scaling up machine learning and deep learning on HPC machines. With Horovod, primarily deep speed is something we already look in the moment. Then we have, of course, not only image recognition, as many of you know, it's of course successful in deep learning and HPC these days, but we have also time series methods like gated recurrent units or here long short-term memory, recurrent neural networks, which are much more for sequence data, right? For things we have in the simulation sciences as well. Not everything are beautiful pictures. Then data augmentation approaches is for those that have not enough data, where we have to see that especially data analytics or deep learning algorithms on the large scale that really require lots of data. So we here and there complement the existing data with some new data augmentation approaches. And then we offer, of course, things like transfer learning, benchmarking HPC machines with some certain AI algorithms, and a little bit an interesting aspect that is essentially relevant for all the AI algorithms is our new research basically on this neural architecture search, where we try to find the hyperparameters in a semi-automated way. It has overlaps with AutoML techniques, but it's really helpful for all the AI models because they all suffer from the problem of not finding the right parameter. So we started with this in the project with so-called fact sheets, which I just will shortly show you what that means and why that is so important as a first step towards the interaction room. It's based on experience from many other EU projects. It's about short introduction of all the major components. It clarifies essentially which codes, libraries, and executables are used, which HPC systems have been used, what basically is the idea of machine learning and deep learning, the areas of interest. So this was our first step that we have now done, and we had a first round through all the applications by now. Just let me show you some 2 examples here of fact sheets from the early co-design examples here in the project. On the left-hand side, you see in the field of remote sensing ideas, how we use, of course, then the Joule supercomputer, basically really in a scalable fashion, at least up to 128 GPUs. We use sometimes, of course, technologies in a data analytics module for Spark, also sometimes with clouds, but also here the D-Wave quantum computer. So you get a feeling from this fact sheet what technologies are involved and what is basically running where. That this not only works for engineering, you can imagine. Here is another example of another paper where we did this also for the health domain. Here's something with neuroscientists we work with, mostly on container technologies, meaning that Singularity, for instance, is available on Joules. We use it there as an example that Exascale technologies maybe also can be containerized. And this is an important part for AI experts. More and more in AI fields are containerized, and this is a quite important endeavor. Here we bridge to the Canadian neuroscience infrastructure, but it shows you again an interesting approach of this fact sheet. So you can combine different areas of use, admittedly a little bit high level, but it gives you a good overview of what really is involved. And then you can always dig deeper what we will do with the interaction room. You see also different areas of science can be tackled. Here we do RDS time series analysis with a gated recurrent unit, also using, let's say, Jupyter notebook technology. So HPC is accessible. For those who are in AI will know that Jupyter notebooks are by far the modus operandi. And so having this available on a supercomputer is very important and will be also provided by CoE Race. And of course, we help there if help is needed, also from Work Package 2. Of course, image recognition goes without saying. The most success in deep learning is basically in this. So we do here COVID chest X-ray analysis of a model there, which is COVID-net and outside in the practice. Good. So in the end, it's not a waste of time. We have been going through this. Just let me share the lessons learned. You see, you can use them also in different areas, in publications, in project presentations, in webinars or seminars like today, but also in dissemination. And it's basically very nice, integratable in papers or other areas where you want to do. So I really think it is kind of a methodology we want to show here, right? And now when we were going through all the different compute and data-driven use cases, you see it's not so beautiful in the beginning, right? So these are all work in progress. This is drafts. We have been through all the 9 to really understand in the first iteration, what are the major needs? What are the systems they already work with? What could be potential AI models? What could be potential libraries to use? And you see lots of work is still to be done, but we have started the project. So time is now there for basically going to the next step, a little bit deeper in all of these different fact sheets. And the fact sheets are, let's say, not here really all of them, all 9, and it doesn't matter. But if you're interested, of course, in understanding more about the different use cases, you can also contact the CoE Race. We don't put them publicly right now. As you see, they're still work in progress. And some of them are actually confidential, I have to say. That's why it's also, let's say, something where we have to first within the project check. But of course, if you contact us offline, there's basically no big secrets in these fact sheets. And of course, a collaboration opportunity maybe for some of you that are also in different areas in this field, like turbulence or wind farm, optimization and so forth. In a way, what we want to achieve with this is a little bit what you see illustrated in this matrix. So we would have different use cases. These are the 9 use cases you have seen. And you have here different AI techniques like data augmentation, I was alluding to, neural architecture search, autoencoder, very interesting transfer learning techniques when you maybe pre-train or reuse a pre-trained network on a, let's say, very trivial area and then refine it for an extreme complex area in science, and many others which are basically on our to-do list to really explore which of the use cases require what techniques. And you see it's a one-to-many association. That's not only, let's say, one model for everyone. This is really an important part as well. As I said, this is work in progress, but we share this early and also want to, let's say, educate the people early about the interaction room process. Just the lessons learned that is really then motivating as the idea of the interaction room. So far, basically, the participants in all the discussions have been quite positive, but we also come from very different fields, right? So there's software engineering experience, there's AI experts, there are HPC experts, and necessarily they don't know each other. And basically also the requirement of HPC's system of a center of core hours getting this. On the other hand, people don't really realize what you can do with AI. And on all of this complexity added, we have the application domain science, right? This know-how which is required. So in the end, we have a requirement for the understanding and communication that is orders of magnitudes here in CoE Race, especially as we want to bridge AI with HPC. And as a consequence, now the interaction room technique is really the technique we're looking forward to get more deeper. The fact sheets were a first good approach, essentially to really get an understanding where we are. And I think with this, I also would like to finish my presentation and would say I'm very grateful that Matthias could join us and also Helmut and share their experience with essentially the interaction room techniques. Okay, so if basically nobody has a very urgent question, I would say, Matthias, just carry on.
Right.
We have enough time later on, right, for question and answers. We have reserved the end of this webinar, essentially just 30 minutes for all of this. In this sense, yeah, we continue then. Matthias, the floor is yours.
Yeah, thank you very much, Morris, for the introduction, and thanks everyone for joining the seminar today. As Morris mentioned, I'd like to introduce you to the interaction room method, which is a method originally born out of the software engineering field, specifically the field of requirement elicitation and early project planning, early project design, based on experiences that we had at the University of Duisburg-Essen, that we had also in a variety of software development projects with large enterprises, where you constantly run into the problem that as you're developing software, and some of this you might recognize already from software projects you've been involved in HPC projects you've been involved in, that the problem is not just building software correctly, like having bug-free software, but building the right software. That is building software that is fit for the purpose and building software that is doing its job, not just correctly, but doing the right job. And this is actually where most software projects problems start already at the very beginning. Most software projects don't fail because people chose the wrong tool or the wrong approach or so, but because there's been early miscommunication between domain and technology experts, which are kind of the two schools of thought or the two big areas of expertise that you have in any software project, whether it's something about an insurance information system or whether it's a physical HPC simulation. You always have experts in the particular application domain and you have experts in the technology. And these two sides kind of need to come together and understand what the opposite side is doing in order to come to a solution together. Difficulty in that is that usually these sides speak very different languages or have very different vocabulary. So there might be a struggle in understanding requirements precisely or even expressing requirements precisely. Because a lot of this knowledge that people are expressing there is not obvious to the other side. Something that's completely obvious to a physicist might be something that needs to be explained to a computer scientist or software engineer. Something that is a no-brainer for a software engineer is something that the physicist might not be immediately catch on to, and vice versa. So we have a lot of implicit knowledge, a lot of unknowns. Some of these unknowns might just be unknown to one side on the table. Others might be not really in the awareness of anyone around that table. So we need to make sure that we realize all those things that are not obvious, that are implicit, that are tacit knowledge, and make those implicit early on, so people don't run into surprises later on when, like, halfway through the project, people say, yes, but this should have been obvious from the start, even though it was obvious maybe only to the domain side or the technology side. This becomes particularly important when we're not just talking about plain functional requirements, so like things that the software is supposed to be doing, because those you realize sometime along the way if the software is lacking in some kind of functional regard. But we have what we call value drivers or effort drivers or risk drivers, which is properties of the software. That could be features, could be quality properties that are particularly important to some of these experts. So the domain expert might say, well, if we don't get down to this level of precision, all the results will be worthless. The technology expert might say, well, if we are talking about this level of precision, that would require us to invest much more effort into computing resources or into the development of algorithms and so on. And so these value and effort drivers can easily become risk drivers, can become aspects that can derail a project if they're not recognized early on. So what we're trying to do is to recognize these things early, like what are really the things that are making or breaking the project, not in terms of functionality, but in terms of like what's really important to us and what are the things that can break the project down the road. It's also important to understand what's fixed, what's flexible, what's variable. So like, where are the things that we can compromise on? Where are the things that we can't compromise on? Where are the things that might be changing? Because anything that is variable, that is like changeable throughout the project, is something that can't just be hard-coded in there, but needs to be encapsulated in a way that we can modify that one bit without having ripple effects throughout our system. And all of these things are commonly something that are more or less visible and more or less obvious to people on one side of the table, but not at all obvious maybe to people on the other side of the table. What do we do in this case? In classical software engineering, there's two approaches. The most classic approach is to have like a big upfront specification. You might have heard of like waterfall models or like Big Bang approaches, where we try to create a specification that is like a detailed document in the very beginning of the project that tries to specify all of this. Problem with that is we're pretty much having the same struggles. We're just putting them in writing, and then we realize later where those documents that we created at the beginning are lacking, because everyone is just like dumping the knowledge into the document, but still not putting down there what is implicit knowledge, what is tacit knowledge, what is non-obvious knowledge. So like we have the same issue. It's just in a document, and whether the document is read and understood at the right point in time is not a given. At least that's experience from large information system projects. People then came up with the agile approach, where they said, well, okay, so if big written specifications don't work because people don't put in there what's necessary and people don't read them at the right point in time, let's just do away with the big formal specifications and work in a more agile fashion, where we are interacting a lot, where we have a lot of feedback loops that make sure that people are constantly like talking about the issues at hand, which is already going in the right direction, but it still provides very little guidance for communicating about what's really important. Like agile methods tell you about like having sprint meetings, having daily meetings, and so on. So they encourage you to talk a lot, but they don't really tell you what to talk about. And this is where the interaction method should come in to give people a bit of a guidance on what they should be talking about. In the end, what we're trying to solve here with this approach is getting to the core pretty much of any kind of software development, that as we're developing software, what we're starting from is always like very fuzzy ideas in people's heads, which they might not be completely aware of themselves, what exactly these ideas entail and how exactly these ideas should be fleshed out. And we're trying to go from these very fuzzy ideas to like the most unambiguous, most precise way of expressing things you can imagine, and that is software code. Like an algorithm is perfectly deterministic, and there's no ambiguity whatsoever in there. It does precisely what it is expressed to do. But getting from that fuzzy idea to that algorithm, that is where software engineering comes in, where software development comes in. And the issue here is that a lot of that knowledge that we have and that is kind of assumed to go into that code is non-obvious. It is dispersed across different people's heads. It is latent, they might not know it's relevant, and they might not even have all the knowledge that would be necessary to perfectly write this algorithm to begin with. Which means that software development is this social learning process, the social process of the whole team learning of what software engineering or for this particular project is about, and what the best solution is for a particular problem. And that requires interaction between all the people, the domain experts and the technical experts on LT. So we need to have this focused personal discussion that agile approaches already encourage us to conduct. We need to understand the application domain and be able to model it in software some way, while recognizing valid effort drivers, while eliminating risks and uncertainties. That is pretty much the foundation of successful projects and any technology decisions, like, so which language should we use, which framework should we use, which software architecture do we use, come after that, because they need to be made, those decisions, based on an understanding of this. And this has been known in software engineering since 30 years, 40 years, which doesn't mean that software engineering has come up with a perfect solution to this. Neither is the interaction room the perfect solution to this, but it is hopefully a way to catalyze some of this thought process. What the interaction room is, and now this is not rocket science either, it is pretty much a room that helps people to communicate by giving them a dedicated space where they can make these thoughts and make these visions of the software explicit. It should be a room that's important where domain and technical stakeholders feel at home. We often have the case in, or at least the experience from enterprise project has been that typically like one of these teams that is leading the discussion does it on their own turf and the others kind of feel out of place. So like it might be somewhere the technical stakeholders, domain and the domain experts are invited, give their knowledge, and then are kind of like pulling out because they say, well, now it's up to you guys to get this done. Which is not really helpful if you're just like throwing requirements over the fence and hoping that the other side will unpack them and understand them correctly. This needs to be a continuing process, which also means that such an interaction room is nothing that is like a single workshop, but it is a place to come back to and have these discussions and to elaborate on aspects as the project is continuing. Classically, and this was like pre-COVID, we did this with a room which had like large whiteboards on the walls of the room, no classic conference table. Like we didn't want people to start sitting down and becoming complacent and like one guy is talking and like the others are checking their email, but everyone really walking around this room and working with the information on these boards, which I'm getting to in a bit. To say, okay, like this is what's important about the processes, the objects, the interactions, the integration in our project. So we want to visualize and discuss the key aspects of our projects informally without going into this document and specification mode. Because once you're in there, it's easy to kind of like delegate responsibility and say, okay, like someone has to write this and then I'm going to review it and maybe look at a few commas. But large documents are not a good way of expressing complex ideas because I tend to bury what's really important under heaps and heaps of trivia. If you have ever read like a 50-page specification document, you know that there is like a ton of text in there and maybe there's like a few paragraphs here and there that contain really critical information. We say, aha, if that's the case, then we need to do something. So like there's like bits and pieces in such a specification that get you thinking, but they're buried under pages and pages and pages of trivia where you say, yes, this is obvious, we just need to have this obviously, but we all know that already. Which means it's easy to miss things in a big specification. While here in the direction, we try to focus specifically on all those things that give people these aha moments where they're realizing things that they need to understand for the purpose of the project. We do this by visualizing the key aspect of the system from different perspectives and at an abstraction level that's accessible to all stakeholders. So we're not providing like or developing formal, specific, detailed, complete design documents here, but sketches that express the key things that everyone needs to be aware of in order to reflect them in their own decision making and in their own, say, technology choices, methodology choices, and so on. For the information system, it has been proven to focus on like the static and dynamic aspects of the system itself. So for example, the application domain data structures, the application domain processes, the components of the system, how they're interfacing with one another, and maybe how the user experience with the system is. Which means all the basic building blocks and their interaction in a system at a level that is sufficient for everyone to become aware of how the system is supposed to work. And this can be relatively high level. This is an example from an information system in the healthcare domain. Not necessary to understand the details of the system, just to give you an idea of some of the processes, some of the structures that have been modeled here. So we're not going down into like deep formal UML diagrams. We're not like fleshing out the attributes of any of these entities here. We are not really looking at precise and complete exception handling in all particular business processes, but we're making sure that people are aware of like, so how does this process work in principle? What information is involved in this process in principle? And then we can go ahead and once we've understood this, go maybe into more formal specifications later on. What we're doing in the interaction room is specifically informal and deliberately high level. So we're deliberately sacrificing everything that normally software engineers hold dear, like formality, consistency, completeness, in favor of having a pragmatic approach that gets that leaves like no people behind who are not that familiar with the UML or who are not that familiar with software engineering. So the key thing is that domain experts and technology experts should be able to conduct the whole meeting while remaining on track and not being left behind in technical or domain details. And if someone's not understanding something, that's the key thing to say, I didn't quite get that, like, how would this work? Or why is this important? That's one of the most important questions in an interaction room workshop. Why do we need this? Why is this important? What implications does this have? How does this work? Not so much like, what's the last bit of detail and the last bit of exception handling in here, but what's the relevance of this? Because once we've understood the relevance, we can kind of decide where to or how to reflect that in our architectures and in our methods. This could be very well that at some point we decide that we need formal specification for some of these aspects, but typically not for all of them. And that's the key thing. We're not trying to spend a lot of effort on providing a complete formal specification, but only for those areas where we really need it and where it adds value. So these sketches that we draw in the interaction room should be catalysts for the identification, understanding, and discussion of what are the most critical project aspects. And that would be understanding domain and technology on both sides. Understanding what the goals are, what the dependencies are, conflicts and trade-offs. So what are the forces that are pulling us in the different technical and methodical directions, and where do we find like a compromise, a middle ground that will deliver the results we need with an effort that is realistic. And what are the things, value and complexity drivers, risk, uncertainties that could derail us on the way. One important technique to help us in focusing the discussion on these things are annotations, which are these little visual icons that in a physical workshop would be little stickers you put on those canvases, or in a digital workshop are these digital icons that you can use in a digital whiteboard solution, for example, and that you would stick anywhere on these sketches to designate aspects that are of particular value to you or that you deem having particular risks. So for example, things that are particularly valuable for achieving the goals of the project, something that is valuable to many users, something that is performance critical, time critical, security critical, usability critical, has legal implications, requires particular interfaces, is particularly complex, requires automation, does not require automation or cannot be automated, and so on and so on. So I'm not going to go through all of these because not all of these might be relevant for HPC projects, but the key intention of these annotations is that we want to shift the attention from what's visible in the model to what's typically invisible, implied, and so on, because those are the things that usually decide the project success. If you look at these models, and if you imagine like much more complex models than these, you might not really realize what's going on in this project. Yes, this is something to do with healthcare receipt processes, but yes, this is a model that doesn't really tell you anything. If I show you the annotations that people put on this model, and this is from an actual industry project, you get a clearer picture for like what people were thinking, what was going on in people's heads as they were looking at these models, and where they were perceiving to have particularly important aspects in there, where they were perceiving particularly critical aspects, where they were seeing particularly complex aspects, where they were seeing legal pitfalls, where they were seeing interfaces to external domains, where they were seeing stuff that cannot be automated but needs to be done manually, where they were seeing things that they would like to see automated that were currently done manually, where they were seeing questions that are still open, and so on. So suddenly you see where probably the complexity lies in this particular project. Without understanding anything about the domain, you get a better impression for things that this kind of, or that this team would have to focus on answering, would have to focus on solving, would have to focus on preserving, would have to make sure is legally clean, and so on. So suddenly we see what probably the construction areas in this project are, what probably the sticking points of these projects are, and where you would expect this team to put particular emphasis on. Probably the things that are most complex. By having just a model, you don't see what's complex, you don't see what's critical, you don't see what's risky. If you see these, you have a much better idea of where the risks are and where the complexities are, and where probably this team should spend their effort. And that is something that is not just put on stickers in a workshop, but should be traced so that this knowledge is not lost, but remains visible in the project. Ideally, for every annotation that one puts on one of these sketches, the team should record, so like, what precisely is the issue in 1 or 2 sentences? What is the complexity issue here? What is the legal issue here? And so on. What impact does it have on the business, or more generally speaking, what impact does it have on the project goals, technically and domain specific wise? And how complex will this be to handle? Is this something that we need to talk about for an afternoon? Is this something that will take us 2 weeks to come up with a solution for? Is this something that the whole project is like pivoting on? That helps us to allocate the necessary effort and the necessary expert resources to addressing these questions. And this is really where the main benefit of the interaction room approach is, that all this knowledge that is usually tacit is elicited very early and is explicitly attached to these artifacts that we're conducting or that we're creating as we're thinking of a project. Normally, in a typical non-interaction room software project, you might draw these models, but you wouldn't have all these annotations. Like, your models would look like this, and no one would know where the pitfalls lie. With this, we have, like, as one of the first artifacts in a project, we see precisely like where the difficulties are going to be. So we have the formal objective understanding of the project, plus the informal gut feeling kind of information that helps us to focus our future work on solving the problems, and not just like building things, but kind of like building around the problems until they are the only thing that's left. And that's what usually happens in large software projects. People start building the easy things first, leave all the problems for later, and then run into problems in the last 20% of the project, which suddenly takes 80% of the effort. That is something that the interaction room is trying to avoid. The workflow typically is that you start by defining the project scope. It's like, what are we trying to accomplish in the very high level? Then filling these canvases, looking at the different perspectives of the project. And Helmut will talk in a minute of how these canvases should look like and could look like for an HPC project rather than an information system, as I've just talked about. After filling the canvases, one would place annotations on there to highlight the different value and effort and risk drivers. Specifically placing these uncertainty annotations, having these question marks in here, is experience has shown like a very important dedicated step to say, well, everyone now put like one question mark on here. And you would be surprised how many people who initially said, oh, this is all clear now, suddenly put question marks in all kinds of places, because they say, well, okay, if I have to admit one question, then I have one actually here. And suddenly admitting not to know something or admitting to be uncertain about something is not associated with stigma anymore, but is just a constructive part of the whole system design process. And then you go ahead and revising these canvases with the new insights, and you can do that throughout the project as you're focusing on different aspects of the problem domain, or as you're focusing on different components of the system. Maybe have some iterations on formal specifications, making a project plan, whether that is agile or classic plan-driven doesn't really matter. The key thing is that the decision-making will, in this phase, in the planning stage and in the design stage, be probably much better informed by all this implicit knowledge that usually was dispersed around people's heads. At least that's something that we found in industry projects in different domains, where as one particularly striking example, we had like one industry project where a typical sprint breakdown would look like this. Normally, kind of the work to be done should follow this line nicely, monotonously falling, but they were just like identifying new tasks as they were going along, which is something that should not happen in an agile project. And the thing is, it turned out that they didn't really understand the problem they were working on, and kind of like figuring out the problem as they were going about solving it, which is not the best way to come up with an efficient, workable solution. And after introducing the interaction room method to this team, their percentage of unplanned tasks dropped from like a quarter of everything they were doing in the system or in the project to like 6% of what they were doing in the project. I mean, this doesn't sound like a lot, but if kind of like a quarter of your work is something that you figure out day by day and it hits you as a surprise rather than something that you plan in advance, doesn't sound like a very efficient way of going about things. So that really worked out in this particular project. So much, I think, for a brief overview of the method. If you'd like to read more about these methods, there's like one whole book about this, focused on information systems, and a paper that is transferring this to the HPC domain, which is also what Helmut is going to talk more about in the next talk. For now, thanks a lot for your attention. I'd be happy to answer any questions and look forward to applying this approach together with you in the Race Center of Excellence. Thank you.
All right. Yeah, thank you very much, Matthias. That was really interesting. I think in the light of the time, we have still some time left. We could maybe have a short comfort break for everyone, about 5 minutes, and then maybe 10 minutes. I would say that's more realistic. So we would probably continue at 5 past here with the presentation then of Helmut. And then we have still a kind of question and answer session, discussion session, how we move from fact sheets to interaction rooms, how we apply the interaction room in the CoE race, how external project partners could be involved, and things like that. So thank you very much so far for joining. Please stay online. We just break for a short time to get an update of coffee or whatever you like to drink. See you 5 past.
So, shall we continue?
Exactly, yeah, we have 5 past. So I think we still have most of the audience. That's very good. And yeah, Helmut, I think just get started and then we have the discussion afterwards.
Yes, exactly. So yeah, thanks for having you back after that break. So my name is Helmut Neukirchen. I'm together here with my colleagues Matthias and Morris, professor at the University of Iceland. And like while Morris is the HPC machine learning guy, Matthias is the software engineering guy, I see myself somewhere in between, like doing software engineering for distributed systems, which includes HPC systems. And I want to give you therefore ideas how that interaction room approach can be used actually for HPC. And after having seen Matthias' presentation, you might think, yes, that probably works well for enterprise business applications, but my HPC code is, of course, not a business application. But my argument is that, in fact, very similar considerations, what Matthias was talking about, applies as well also to HPC. Like we have different assumptions as soon as we have more than one stakeholder. And they have different knowledges, and you probably want to exchange these knowledge, not that each becomes the same expert. Still, you need different expertise in different area, but you need to understand the other. And that is also what here we have in the Center of Excellence race, essentially. Like we have different experts working together. The machine learning guy wants to talk with some simulation guy, and they need to know what the others can offer and how they can work together. And in fact, like HPC projects, at least scientific ones, they very often start with one single domain expert. That might be some engineer or some other natural science, some physicist or whatever, writing HPC code. Like that could be an HPC student, and being an PhD, that could be a PhD student, and being a PhD student like in physics means you maybe did a little bit of some programming education, but not deep education in HPC or software engineering, or maybe AI or machine learning in general. And then, yeah, more or less the same problems, that as soon as you are not alone anymore, but work together with someone else, then essentially the same problem occurs at different occasions. Like think about having a PhD student with a temporary contract, then like after 3 years, that PhD student finishes and has to hand over the code to maybe the next PhD student. And then of course, the first person has a lot of knowledge about the code and about the problem as a whole, has some implicit assumptions, and this new person takes taking over somehow needs to learn about that. And that is an example where the interaction room could help. Or sooner or later, that domain expert, I said, no strong education in computer science nor HPC, sooner or later the person struggles with HPC problems, the code does not scale well or whatever. And then the code needs to be handed to some HPC expert at a supercomputing center. But of course, that HPC expert, well, knows a lot about HPC, but not about that particular problem that this code is about. And then again, these people somehow need to talk to each other and knowledge needs to be transferred. And as said, essentially, we have the same here in our Center of Excellence race. And therefore, the question is, yes, for what can you use the interaction room in HPC projects? And essentially what we have, like we have that guy here from some natural science or engineering domain. And we have here some guy who could be from some HPC domain or AI specialist or in general computer scientist or software engineer. And these somehow should talk together. And therefore the idea is we adopt the proven interaction room concepts. However, of course, all the canvases that Matthias mentioned that are suitable for enterprise applications, they of course need to be adapted to the needs that are specific to HPC or AI or machine learning in general, or a combination of these. And then the idea is that then suddenly that single person or these single persons then suddenly start talking together, as we have learned from the interaction room approach that Matthias presented. And of the whole point, as you learned, is of the interaction room is like making people talk about critical issues. Like what are discussion points that are relevant for all the disciplines where they work together. Of course, still like the physicists works with their physical equations. You as some HPC expert do not need to know how does the equation itself look like, but you need to know which solvers do you need to solve them and so on. So essentially, like, yeah, these discussion points that are relevant for all disciplines that somehow need to be covered, and then the phases that you typically have in HPC software development or in software projects that involve AI at a large scale, so that you need in the end some HPC center. And in fact, these are already different whether you do classic HPC like simulation sciences, what we did don't know since decades, and now since a couple of years we also have these data sciences, high performance data analysis, or AI or ML. And so far what we did, so there is that publication here from 2017, what we did there was introducing canvases for the classical simulation sciences. So this is what I show you next. But as said, the idea is to use this interaction room approach to foster collaboration here within the Center of Excellence. And there we need to go beyond what we have published so far. So like we do not only need these canvases for HPC, but also for AI, and very likely, or in fact, that is the core of this project, for the combination HPC with APIs, or classical simulation sciences with AI combined. And like I mentioned already, what are like crucial points where the different disciplines come together in such projects? Like on the one hand, it's then that science, natural sciences or engineering domain expert who needs to help like the HPC expert or the software engineering expert or the AI expert need to make that person understand what your like simulation is about, like which research question are we trying to answer. I will later give you examples how this would look like given different canvases. Then like maybe assumptions and simplifications that are made. As said, as the other experts, they maybe don't need to know the details of the underlying physics. Still, they need to know what are parameters that influence the simulation, what are the variables, how do they affect each other, how do they evolve over time. And after having gotten some understanding of that research problem, then the HPC expert then probably can help like turning this then into a parallel application. It of course also depends, like whether you do that rather from scratch, like some physicists saying, I want to parallelize this, hey, HPC expert, tell me how to do that. Or as I described earlier, you develop the code on your own, and then at some later stage in your project you have problems. Then probably it's most often the HPC expert says, show me your code, but maybe in the beginning you don't even have code, so there are different approaches to that. But the point is then in the end, the HPC expert can then make suggestions. Okay, this needs to be run on GPUs, this needs to be run on CPUs. So essentially technical decisions are made that need to be validated. And again, there the HPC expert needs to talk to the domain expert to take care that no misunderstandings are there, to achieve that implicit assumptions are made explicit. And as said, these technical decisions might be about how to parallelize things, how to do the domain decomposition, or like what hardware is best suitable, CPUs, GPUs, is this something that needs a lot of RAM, or maybe rather fast CPUs, but not a lot of RAM. So what you typically nowadays have is this heterogeneous or modular supercomputing, different modules suitable for different problems. Then when you parallelize things, then you can have like distributed memory, shared memory, or hybrid approaches. If you have distributed memory, then you need to communicate with each other. So what MPI communicators do you use there? You typically need this ghost or halo regions when you do the domain decomposition, so that one cell somehow is influenced by the neighbor cells and vice versa. So all these are then the technical things that an HPC expert then maybe talks about to the science domain expert. And to support that process, we assume some general software development process that is going on there. In practice, that might look slightly different, but I think in most of the cases, it starts that everyone needs to understand the problem domain. As I said, this could be the engineering problem that needs to be solved or simulated. So what is the general goal and scope, but also details. So it might be there is maybe already some serial code solving that problem. And looking at that, then the HPC expert can then maybe decide how to parallelize that one, which is then essentially already the next step. Like, how do you do the domain decomposition needed for parallelization? How do you do communication between processes or threads? Which is then already the next step that would then be mixed. Like if you have already that serial code, then you somehow need to break it up so that you mix in this parallelization into that code. And once you have running code, then you need to test it and validate it by running your simulations. And then in the final step, then you either tune the performance, doing some benchmarking and tracing, identifying bottlenecks, maybe optimizing accuracy using better solvers or whatever. In particular, the performance aspect that can then be specific to hardware architecture, or again, could be like mapping it to a particular heterogeneous module of your modular supercomputing architecture. And therefore, the idea is that we support these different steps using specific canvases in that interaction room, like canvases, as I show you on the next slide. How does the program look like in general? What are the details? So these are then more from the problem point of view. The others are then more the HPC ones from the technical point of view. And again, we use the same interaction room approach. So in pre-COVID times, as Matthias described, that was really putting people into the same room and making them talk to each other. So that's essentially the whole point. But as Matthias pointed out, it's not just so, oh, well, you somehow need some catalyst. So maybe there's the elephant in the room where anyone knows about, but no one talks about. But as Matthias pointed out, if you force everyone to put a question mark, then you suddenly find out what are the problems that people have, either different problems or everyone having the same problems. But I also want to point out that these canvas types that I describe here, these are not carved into stone. So these are whatever fits your purpose, whatever helps you best, you're welcome to use a suitable canvas. These here are just suggestions that we made here that are suitable for simulation science HPC projects. And as I said, the first canvas is about describing what you start with, describing the problem from the science point of view. Then the next one is going into details of that science point of view problem. And then we rather than switch over to the HPC perspective, like how do we do the parallelization? This is the decomposition canvas. And how do we map this then on some particular HPC hardware? And as Matthias also mentioned, so this is not necessarily some sequential flow, but rather you have iterative refinements you learn while being in the interaction room. You add what you did draw there on these whiteboards, you add these annotations. So it's a learning process. And like to give you an example, like I said, the first canvas that we start with is that problem canvas where we describe what is the research question that should be solved by that HPC code. What are boundary conditions? What are simplifying assumptions and abstractions that were made? Also maybe quality requirements concerning precisions or something like that. And I have here as an example some heat dissipation problem, like the research question there would be like, yeah, here, what will the temperature be in a room after running some air conditioner on one side of the room, a heater on another side of the room, running that for several hours so that you reach some equilibrium. And then you have boundary conditions, which might be like, of course, the starting temperature of the air in the room, the temperature settings for the air condition and the heater. Then abstractions that you talk about could then be like we only talk about airflow and convection, but not like radiation or something like that. Assumptions are we don't have any moving objects or open windows or things like that. And quality requirements might be like we want to have double precision float numbers. So this would be the very first thing, like a scientist comes to some HPC or AI or whatever expert and needs to tell what is my problem about. And after having set that generic general problem, we can then go into the more details. What in simulation sciences, where you simulate the real world, would be what we call the real world canvas. So going more into details of that. So this is then where a physicist would then talk about, okay, if we have a radiator here, an air condition here, then we have the following physical processes going on based on some physical laws. Like what are spatial aspects? I said this might be where are the radiators located. And then in addition to the static properties, you also have dynamic properties, forces that are involved. Events, well, here I mentioned we have no moving objects, but of course you could have events like doors are being opened and things like that. And then again, for the particular example of the heat dissipation problem, that might be like spatial aspects, like what is the room geometry? Where are these heaters and air conditioners located? Yes, how does the convection work there and the airflows, and what are their according physical formulas for this problem? And this should then be hopefully enough for the like HPC or AI expert to understand these problems. But as Matthias pointed out, we can then use like annotations, like forcing people to put these question marks somewhere to solve as a catalyst to really point to the problems where maybe like the domain expert from physics, of course, knows all about physics, but the HPC expert not. So having different implicit knowledge and making clear where one person is lacking this knowledge to be able to make that knowledge explicit or these assumptions. And then we rather switch then more to the HPC aspects. As said, we assume here like we start from scratch. Rather, if you have like existing HPC code, then I said it might be very often that the HPC expert simply tells the domain expert, show me your code, what you have so far. So that might also be an aspect to discuss here. But here we assume like, how would you do then the parallelization from scratch? Like this would be static aspects. How do you do the domain decomposition? Which data structures do you need that maybe fit the used domain decomposition using some grid mesh or something like that? Dynamic aspects would be about like, how do you do communication using certain MPIs, getter, gather, and whatever. These halos and ghosts that are needed to do the domain decomposition, like values there in the neighborhood that influence the cell that we are currently calculating. Maybe we need to change our mesh in an adaptive way. We may need, for those equations that you cannot solve directly, you may need some iterative numerical solvers. And again, for the heat dissipation problem, that might be, yes, we use adaptive mesh refinement, we use halos, and we need some Cartesian communicator to exchange data between the different cells of our mesh, and we need some iterative method to solve there some equations. And then the last canvas is then like mapping this then on the suitable HPC technology, like the cluster architecture, like kind of memory models, non-unified memory or whatever, local memory faster, being faster than other memories. Also tools like in the simplest case, just the queuing system used. And then dynamic aspects about the communication, about I/O, and maybe checkpointing to be able to recover from crashes and then restarting. And then like, again, for our particular problem, that could mean like we use 1024 fast CPU cores. We use a hybrid of MPI and an OpenMP. The solver is a Jacobi solver. We use like HDF5 parallel IO, and we do checkpointing every like 2000 steps or something like that. So that would be an example how you can use these different canvases to get people talking to each other and then identify problematic issues and, yeah, discovering implicit assumptions that one person has, but the other does not have. So to come to an end here, so this means the idea is to facilitate the collaboration of all kinds of different experts. As said, the domain expert, the HPC expert that maybe knows all about parallelization, then the AI expert who may also be an HPC expert, but maybe not. And you may even nowadays, you need things like easy build and version control and whatever. You need all kinds of software engineering aspects also in HPC projects. So also, but the software engineers then maybe have no clue about HPC or the physics underlying your simulation problem. So all of these should talk together. As said, these canvas types that are presented, these are not set into stone. So whatever serves as a good catalyst. So that should have become clear. The whole point is the interaction room being a catalyst, forcing people to look at problematic points and forcing them to exchange assumptions and implicit knowledge. And what I want to point out is that while we will use that, I have that on the next slide here in the Center of Excellence RACE work package 2 to analyze the different applications. The fact sheets were already a starting point. But the idea is that this process, as said, we so far have those for the simulation sciences, but not yet for the AI. So creating this would also be an outcome of the Center of Excellence RACE itself. And the idea is that it's then also used outside and beyond the time span of that Center of Excellence by far more experts from all these different fields. So as said, while we have those canvases for HPC, we still need to develop those for AI. And I think, like I said, Matthias, the software engineering and action room expert, Morris, the HPC and AI expert, and me somewhere in between, we will sit together and think about that. And as RACE is about combining HPC engineering simulations and AI, it's of course also canvases that combine these different fields. Also having to think about suitable annotations like the question mark. That is something that applies probably to all, whether it's enterprise business applications or HPC or AI applications, to point to things where people have not a perfect understanding. But the other annotations that Matthias did show, they maybe do not fit that well for the HPC AI domain. We have to think about what are suitable annotations there. And then the idea is that we in future do interaction room sessions. Due to COVID, of course, this can only be virtual, with then individual partners that have their applications. So inside work package 2, we will do this then to get an idea where AI can help these simulation sciences. And that would then mean like we use some collaborative whiteboard software to make people work together. And of course, some video conferencing solution like Zoom. But of course, we will lose a lot having video instead of being really together physically in the same room, like body language that you maybe don't notice, in particular if people have switched off their their video, which can be in practice in a real physical interaction room, then you see, okay, that person looks like he does still not understand this. So that, of course, is lost. So we need to be aware of that. And of course, while the interaction room is a nice approach, it does not help if the people do not talk to each other. So we all are probably somehow nerds and have problems with that. But giving people a canvas and maybe people drawing but not talking with each other does not help. So, but the idea is, as I said, these canvases that serve as a catalyst pointing at the problematic things, having canvases for obvious things that you don't need. Matthias mentioned this 50 pages specification document where then maybe one page contains the interesting thing. So the other pages, they need probably to be there, that information needs to be there, but that is obvious, but it's more pointing to those things that are interesting, that are about problems and different knowledge and assumptions. So this is the idea of how you can use this interaction room in an HPC setting. Matthias pointed already out that we have a publication on that one. And this is what I wanted to show you. And now I'm ready, and Morris and Matthias as well, for your questions or comments on that.
Yeah, thank you very much, Helmut. Very nice. Okay, so I think we have time enough for questions. I would stop maybe the question session 5 minutes before the full hour, because I have an announcement also in the thanks, but feel free to now shoot and yeah, basically speak one after another or raise your hands. That would be probably the best model. In the moment, I don't see a raised. I see Andreas Lintermann. Yeah, please go ahead.
Hello, everyone. Thank you very much for the very nice presentations. I was wondering, because we already started with the fact sheet process and we have already collected, let's say, all this interdisciplinary information, how this can be included in the interaction rooms. So will this be part of the first canvas, or how do you see that, this integration?
Yeah, so
yeah. I was just thinking it could be part of the project goals canvas, like that very first canvas. I think that's a good starting point to kind of kick off that discussion.
Yeah, exactly. So this is not contradicting, but that might be how that first canvas maybe looks like. I said these are not carved into stone.
I think it's still also a kind of survey what elements matter, and we have seen here and there where this interesting flow diagrams where kind of we would essentially prepare the interaction room with the fact sheets already, so saying these elements matter. How we then put them in the flow is already part of this fact sheet, but then we would detail them, right? And would go in AI models with TensorFlow. What does that mean? So what AI models matter to you? And what is the data? What is the data structure now? So we kind of elaborated this a little bit, but I see it essentially as a first initial flow blueprint on different canvases, maybe even. But basically then really looking in each of these blocks more in detail. Not on all of them. We see praise is, I mean, a more, let's say, infrastructure setup. But when we talk about joules, are people using which one of the booster or the cluster model more? Do they use basically also maybe parallel file system? We learned some don't. So essentially, I think the idea is firstly to get an understanding of each other. That is helping with the fact sheets, which already resolves lots of the discussions usually in an interaction room at the start. So people can prepare with these fact sheets and come well prepared to this, also with this seminar today. And then the second idea is really taking these building blocks already and pre-fill, so to speak, very quickly the canvas to really go into detailed discussions. That's how I would see it, but we have to do it, right? So that's definitively now something for the next months. Initially, we planned for having the first results on this in our first deliverable, I think month 9, where we then would, let's say, have an idea which of the use cases have common requirements, right? One of the ideas is then also to think about how on all these 9 use cases and maybe collaborating use cases that want to take up some of these methods would have common elements required, common pre-trained models for AI, common requirements for neural architecture search. So this would be also something which is in the interaction room then perhaps one of the diamonds you had, Matthias. So indicating and annotating, hey, well, we have seen that in other use cases too. So this might be something where we focus first on, because essentially more use cases than less can benefit from it.
Mm-hmm. Okay, thank you. Maybe another question, or another comment. What I see then especially challenging is probably that we don't have in these actual interaction rooms not only two kind of specialists, not only people coming from AI and from the domain, like we did it for the beginning now with the use cases. Yeah, you, Morris, as an AI specialist and also with an HPC background, met the people from the domains and discussed with them, yeah, to work on these fact sheets. But in the end, there will also be people coming from AI background with no experience in HPC, for example. Yeah, and also like this, for example, you have the software developers that are very good in software developing and designing a software, etc., but are probably not so aware of the HPC capabilities that they can use, yeah, or how these HPC concepts can flow into the use cases, can be used in the use cases. So this is quite challenging, that there are not only these two groups that we put together right now and also in the proposal stage, but we will need to include more people and have to be aware that some people they cover only like a niche of the whole problem. Yeah, but we have to include them all, and I think the interaction room is a good strategy to tackle this.
Yeah, and I think we could even invite here and there experts from various different fields where we know, right? That is one of the ideas of the fact sheets again. So we know, for instance, one of them has requirements for singularity. They're already using containers. So we would invite specifically for this meeting someone who is doing this regularly in the Jülich Supercomputing Center, for instance, and using singularity, just to share, you know, and have experience already. What can you do, what not? Or data-led, which is a seminar we do in May, and another idea. So what we do with the data and so on. I think it's not really static, these interaction rooms, and it's probably not only one big meeting we talk about. It's rather an iterative approach where we do, you know, we realize in the first meeting, hey, we need another expert. We have to invite next time because we cannot be expert in everything, right? But what we want to do is quite tough, to have the HPC intertwined AI and there's on Exascale and then on top application use cases. So that's quite a mouthful. So we have to find the right good people. And I think lots of people that are not directly involved will help us there. Helmut, Matthias, I know you have, Matthias, some experience from industry. I guess it was very similar in these areas, right? When you did, you know, these systems with Adesso and so on.
Yeah, so you always have the problem that you have like people from very different domains. And I think, as also like Kurt is mentioning on the chat, like even within those fields, there is not like these two sides. You have like more than two sides at the table typically. Like even within the domain, there is different experts on different things. Even on the technology side, there's different experts on different things. And getting all those to be on the same level of abstraction and on the same line towards solving the problem is important. And that is something really where the tool should be able to help. But as Helmut mentioned at the end of the talk, it's a tool. It's not an algorithm for solving the problem. It's a tool that should facilitate solving the problem. So that is something that probably gives some guidance and structure to the problem-solving process. But that process will still be a creative engineering process. So in that regard, there is no automatic way by which you put a problem into the interaction room and find a solution. That is still something that the engineers and the experts need to think of and innovate on. But the hope would be that this is, yeah, channeling that innovation in a more efficient way than usual.
Okay, then Maria has a question.
Yeah, I really like this tool, and actually many thanks for having gathered us together today about this. I'm just wondering now, in terms of next steps, what would you like to see in the next few weeks concretely, so that we can, how can I say, translate some of these ideas into actions? How can we help? And I'm talking here as a work package leader, so I would like to help. But...
Well, yeah, from the perspective now from work package 2, the next weeks are basically pretty clear. Firstly, we would finish the fact sheets. We had the first iteration with every team, basically, and we would polish these fact sheets a bit more out. At the same time, we will schedule interaction room meeting, the first interaction room meeting, but with every single use case, right? We had it in the fact sheets also with the different use cases, because they're completely different from each other.
Yeah.
I mean, even if they use HPC and AI at some point in time, maybe we have seen some have even 3D printers to generate something. Some other have, an LHC around the corner, like you in CERN. So it's alone on the data side for your work package, it's already very different from each use case. But then also the ones from the compute domain are very similar. It's also there might be a little bit an engineering CFD bias here, I would say. Definitively, there were more applications in that area, but we have also some others. When we think about seismic imaging and so on in your work package, it's also going into interesting dimensions, combining then simulations maybe with data. But the concrete action is really finishing the fact sheets. Then from that, we will fill the interaction room, so to speak, with the Canvas first elements and have another meeting then with all of these different teams in order to prepare well for the next steps. We already came in the fact sheet meetings to the conclusion that the AI part is often very underrepresented, at least in the compute-driven use cases, but also partly in the data-driven use case. And we have to go there much more deeper. Also the data part, especially in your case. So where is it stored? How it is accessed? What quality? Is it parallel IO? Is it not parallel data structures where, for instance, something which was completely underrepresented. Some here and there had their own formats when we were discussing the fact sheets. But this is definitively something where we also have then in this interaction rooms, the idea to break down more deeper. So preparing for some of these details for this interaction room to be, let's say a little bit more on the domain of deep learning or machine learning clear. This could be interesting AI models. Do I have sequence data or not? It's clear that you cannot explain all of them. So we plan also with a seminar series here to every now and then do maybe a seminar on, let's say, sequence data analysis with GRUs or with LSTMs, or basically also a technical one, which we have next time about data-led. So how to manage data, how you keep it active with Git-based solutions for data management, things like that. So I think this is where the helper perspective of work package 2 to work package 3 and work package 4. But I see, especially with the AI part, there needs to be lots of things done in the next couple of weeks to get more clarity. We had the initial metrics we put in the proposal where we already indicated this, and now we have to fill this with life. Is it really true? Data augmentation is a big strategy. What data augmentation strategy I want? Neural architecture search can be done on Bayesian methods, evolutionary algorithms, or reinforcement learning. What technique we want to do in our neural architecture search. So I think there are lots of details, right, which is, of course, not captured in the fact sheets, but what should be now explored in the interaction room techniques over the last couple of weeks, even months, I would say, right? So we have a 3 years project. Nothing has to be all finished in the next couple of weeks. So, but to get a first interesting understanding of where we're going, I think is pretty clear.
Thanks, Maurice. That was useful.
Yeah, maybe I should also add, when I do my finishing slides, I will show it. Of course, we are very open also for suggestions of these topics here. I discussed this already a little bit with the project office here. I discussed a little bit with dissemination that we can also drive a little bit of these seminars based on the interaction room points, right? When we experience, okay, we are interested in neural architecture search, then we give a seminar, maybe not in May because there we do data-led, but in June or July, we can do then a neural architecture search seminar, and I will have different experts. That will be not always Matthias and Helmut with me here. So there will be different experts that do this already or basically have experience in this. And we have lots of contacts that can do this. But of course, just making it for everyone, some some interesting seminars which maybe or maybe not taken is a bit boring, right? So that's why in the interaction room, we can identify topics for the next couple of months where we do these monthly seminars and then really pick one topic in detail. LSTM's completely understood, maybe not for languages like it is often applied, but more for scientific data. For instance, scientific time series, which are actually different than many others. Just to add to the point that, of course, this I see also in the next weeks to see how we can adjust what is relevant also maybe for this seminar series here. Andreas, you have again the hand up, or is it still the old hand?
Sorry. Yeah, it's again. No, it's not the old hand. It's a new hand.
Okay.
So what I see also very important here is that, like you mentioned, there will be many interaction room meetings, let's say, with the different use cases. That there will be at least one person participating in all these meetings. That this information is brought together at a central point, and that the more generalized approaches can be identified or common problems. Yeah, this is what we really want to achieve also in the unique framework that you were talking about. Yeah, to generalize the approaches, to bring things together, and but therefore someone has to be there centralizing these information. Maybe that's just a comment. And maybe this can also then be talked about in, so we have this technical coordination board with technical experts in there coming from the different domains. This could be part of the discussions going on in there. And this should be pushed by the scientific coordinator.
Sure. So of course, we make sure that Work Package 2 people will be on board of all of these meetings. I would not say necessarily one person can do all of them meetings. There might be sometimes sickness, but at least keeps up to date. I myself see that, of course, as well for me as Work Package leader. But I know I have already done some Work Package 2 meetings, so we have some very good people also on board in Work Package 2, which will be joining, I think, many of those meetings in the future. But we're also very lucky that I saw some overlaps, right? So people have been already automatically involved in 2 or 3 use cases here and there. Already in the fact sheets, and so this is then also something where we quickly explore synergies.
Mm-hmm. Maybe regarding the question by Kurt on the chat, like if a virtual reality environment would be good for the interaction room, I think that's an interesting thought, and it's indeed like something that we've been thinking about for a long time, like what would be a suitable digital representation of the whole interaction room experience, really. And one of the guiding principles has always been that it should be as accessible as possible and as low tech as possible, in the way that if you're all in a conference room, it's easy to just like pick up a pen and start scribbling on a whiteboard. And so the technology we're using should not inhibit that process of really getting thoughts onto the board, like getting thoughts explicit. So what we're looking for is really like a whiteboarding solution, like a digital whiteboarding solution, now that we can't meet in person, that has that same or close to the same level of intuitive use and immediacy. One problem I would see with using a virtual reality environment is that it pretty much like requires a larger technical entrance barrier. And also, as long as you can't really like see the other people in VR, like as you would see them in real life, it wouldn't add that much to the experience. If you just see like people's hands hovering around in VR, then you're not gaining much more than just seeing their mouse pointers on the whiteboard. It is true that, as Morris mentioned, or also as Helmut mentioned, the body language in a physical meeting is telling you a lot. Like when you see them first just like being like this the whole time, and you see, okay, they're not buying this thing, they just explain to them, that tells you that there is something that's a potential like risk or effort driver in there. If they just like have a problem with the way that you say this is a solution and then they just don't think that's the case, that means, okay, that's something we should ask about to make sure that there is no point that's overlooked there. Or if you see that the whole discussion is like focusing on one whiteboard, but there's one person still like stuck on that other whiteboard and like apparently having a problem with what's going on in there, or being able to like point to different things at the same time. All that is something that virtual reality would have to, or would be suitable to present if everyone had the setup of having like a camera at home and like being able to like show what they're currently looking at. While that's not the case, I don't think the VR environment would add that much, unfortunately. So I think the what I'd be interested in looking at is like a very smooth shared whiteboard experience, like Microsoft Whiteboard, like I think Miro board, what Morris proposed. And this would in fact be, so in that case, we're breaking new ground here. The first time that we're using this approach like at scale in a digital environment. Normally in an enterprise environment, we're going out to companies and doing that like on site with them so that they are in their familiar environment. And we have this whole physical component of being able to see people interacting with each other. Of course, it's possible to do this occasionally in the digital form, but now would be the an opportunity to explore to go all digital with this and then to really do that at scale. So for that, if you have suggestions for like a whiteboarding environment that in your experience has worked extremely smoothly, extremely intuitively, while still letting people talk at the same time, we would also be happy to see like your feedback on what has worked for you in the past. Like for Boris, I think Miro has worked. For me, Microsoft Whiteboard has worked. Different people might have different favorites there. The good thing about the method is it's not tied to a particular tool. So anything that helps you to sketch things and lets you like move little pictures like for the citation stickers around would work as a whiteboarding solution. The more critical feature would be that it gives you that immediacy of communication like you have on Zoom pretty much, where you see everyone on Zoom at the same time on the same screen. So you can also see at least in people's faces of the 12 people on screen who is currently frowning, who's currently nodding, who's currently like disengaged with the conversation. So that at least is something that's important to be able to transport in a digital interaction room session. But definitely it's an idea that we have been toying with for years indeed, like how to get this digitized in a way that really captures the whole physical environment. And VR could at some time be a solution for that.
Okay, while you're answering so nicely, Matthias, I myself have also a question. It's a little bit about versioning of these canvases. I could imagine that we would, have, let's say, a CFD simulation, and we want to have a surrogate that we discussed, for instance, in the wind farm modeling, and we do some specific technique for the surrogate, but it doesn't work out. So, I mean, this is what we model. Then we have the canvas there. We know probably which library is doing this, but we have to roll back. And I guess similar with the fact sheets, we will have different versions of the fact sheets. That was project experience, tell me, in the last 15 years. How do you deal with this versioning of these canvases, and how do you ensure that they kind of work then together, because it's different perspectives and they need to maybe take into account updates from A and B to stay in sync, kind of, so to speak, right?
Yeah, that's actually one thing that works better in the digital interaction room than the physical one. So because with the physical room, we always have this problem, okay, the meeting is over. What do we do with the room? Do we take pictures? Does the next person coming into the room erase everything? How do we reconstruct it then when we want to pick up the work again? For the digital room, I think it's very nice that you can just like save the state that you are at the end of every meeting. And I think that's like a good checkpointing interval to just say, like, at the end of a meeting, we save that version of the whiteboard so that we can then return to it either at the next session, or we can branch off of that in the next session. But at least you have these saved checkpoints to get back to. So that's, for example, something you can do in Microsoft Whiteboard. You can either have it living there in the cloud and you can like come back to it, and also like you can asynchronously come back to it whenever you say, oh, let me see what we talked about yesterday, and I'm going to look at that particular aspect of the whiteboard. So it's always there in the cloud and people can visit it at their own convenience. But at the same time, you can save versions of it and then like reconstruct versions of it. So that is definitely a good practice at the end of a session to save the current state of the whiteboard, so you can see maybe how an idea has evolved and to be able to backtrack if necessary.
Okay, yeah, thank you very much, Matthias. Looking forward to see how that all works. Any other one maybe here on the call that has any question? Still a little bit of time, so no problem. Going once. Going twice. 2.5 really. Okay, if no one raises a hand and no one has questions, we can maybe wrap up a little bit in the next couple of minutes. There's a chat question maybe. Okay, that's from Matthias. Okay, excellent. Right. So, I mean, first of all, I would say thank you to all of you joining, in particular light of the fact that we changed the registration at the last minute. We wanted to do some statistics also who is actually joining here, and this is of course quite useful for us in the project. Also, if you have suggestions about possible other topics you want to hear from us, we basically could think about singularity, how to work with this, and containers on a HPC machine, how to use a particular AI model and train it, you know, sequence or image-based models. We could think about Jupyter Lab, how this works in HPC environments, how you get this with your, you know, science going and with a scheduler. So this is, of course, a kind of interactive approach still in line with scheduling. So these are things we can do, and also particularly adding new kernels maybe to the Jupyter Lab, which is very interesting because then you can combine the power of module loads with essentially the Jupyter Lab environment. As I said, we will talk also about data lab, and this is now what I would bring you a little bit as an appetizer here. So if you have to have more information, of course, please go to the website, and there you find also the contact. We also, I think, quite prominent on all the social media platforms. So please follow us there. But if you want to be involved in one of the use cases and your project external, it would be also good to really contact us. There's maybe possibility for collaboration, in particular light of the fact that RACE should be also, you know, get an uptake by user community, should be also used by more the things that we do. Now, just as a short idea what's coming next, you see here, there will be lots of technologies which matter. And as I already alluded to, data-led is one that we consider maybe as part of our software infrastructure that could be quite interesting. Hence, I would just give you a small appetizer for the May seminar. There is no date yet. So we will basically do a doodle within the project, but then we'll open up, I guess, this event also to the community in HPC. So if you're a project external right now, you also then can participate. And just give you a couple of slides before we close here, why this is maybe relevant for you, this data-led technology. It's basically a data management tool, but unlike many others, it has an interesting idea that it's built on top of Git, right? So it has a versioning approach to it, which makes it quite interesting and quite nice. So essentially, we could put the canvas that Matthias mentioned in as data and then keep the versioning of this canvas done. So it's really an interesting approach of data management. That is not to say that we definitively will need this and do this in all the use cases in the project, right? So I've seen some of them have already their data management solutions. Some already know how to handle data. But when we think about here using, for instance, different AI models, and then have also the runs of the simulations, we should not forget, and different ones, we maybe can benefit from this system. So it doesn't mean that it stores basically all the big runs, which are terabytes, maybe even when you dump it, basically then somewhere in the cloud. It's rather more the index and the kind of versioning that is controlled. So still the data lies in a proper file system location. However, it could just help a little bit to get the overview of, you know, who was modifying the data set, what is the versioning of all the different AI models and the accuracy rates compared to something we maybe also want to publish. So it is a nice tool, essentially comes also with a command line tool, what we will then demonstrate a little bit, of course, with, let's say, a trivial example. And it has many other smaller features that you would consider may be useful, which could be basically all the provenance metadata aspects of it, right? So it has search, metadata search. It has a way of publishing and sharing the data, which might be quite interesting, especially if it's large data sets. You don't want to do it in something like a Dropbox, right? And then from the Dropbox back or something like this. So when you want to share something, this could be something to think about. Okay, so, but not to make it too long, this is also a quite flexible tool that you can use for many other things. You know, for instance, that we also think at one point in time about real code, right? Real Python code for AI models, but also maybe intertwined with already C or even Fortran codes I was listening to in the fact sheet discussions. So essentially, this could be also for codes, for data, for scripts, for scheduling scripts. So lots of things we will generate. And my experience also for many other EU projects in the past is that gets quickly diluted and lost. So we have to think about that. At least we have a Git. In Work Package 2, we already started this a little bit with the FZJ Git structure, but also project-wise, when we think about this data sets and so on, it would be quite good to have the system there. So we have to see how that works. I know currently we're using it with the neuroscience community, quite successful in Jülich and also more internationally these days. And if you want to know more, of course, you can also go to a very nice handbook here, basically that is provided by DataLad itself. But we would offer basically in May timeframe also kind of a 2 hours short introduction. Of course, we cannot cover everything in 2 hours. We will have speakers from the DataLad team that already knows a bit about it and also how we do it in Jülich. And it's one potential basically we could use. Here's one example how we use it in Jülich, mostly for, as I said, in the neuroscience community and medicine, where they have also very large data sets, right? Like CFD simulations, or when I think about the LHC data. So these are things we want to think about. And on top of it, of course, now all the AI parts which come close to it, which means different models, pre-trained models, we want to keep maybe in different versions, justifying also that we basically have then a kind of nice track what we have done and can publish these directly. So there's a possibility also to have a direct provenance part of it, which makes it also interesting. So I just put that here essentially as a small appetizer for you. Of course, I will now basically not go in all the details on this, but you get a short overview what you can do with it. You discover, consume, publish. Reproducibility I didn't talk about much, so there's a possibility also to enable this when you consider kind of pipeline, maybe where you want to use different types of pre-trained models for transfer learning, and then maybe make an investigation about it. And I think that is all quite an interesting technology. But as I said, what we then do in June, in July, will be probably crystallizing out of the interaction room seminars. We will maybe have different AI models or containers or Jupyter Labs. The date and time will be announced. The recording of this seminar today will be available on the YouTube channel on CoE Race. The slides will be also made available. I'm not sure exactly how we do this, probably via the website. We have to talk about it, otherwise you have the video. And yeah, so that.
Yeah. And for those who are in the CoE Race project, the slides are in our BSCW server.
That's a good point. Thank you. Of course, we will upload the slides there also. All right. Yeah, so I think with this, we probably can close the event today, unless there's any final statement. I don't know, maybe from project management, Andreas, as our coordinator, you want to still say something?
I have nothing special to announce. Yeah, but we were also thinking about having additional seminars on the HPC systems that are involved in our project, yeah, to introduce them to the developers in the project. And there would probably be a joint workshop on in situ processing with a CoE combustion, yeah, coming up. But it's still in the planning phase.
Yeah, these are interesting topics, absolutely. Of course, I'm a bit biased from my work package, so we have a broader project here, so that's why I thought it's good that Andreas talks a bit. But yeah, thanks again for everyone joining us today, and see you next time.
Thank you. See you.
Stay healthy, everyone.
Bye-bye.
Thank you very much. Bye-bye.
Bye-bye.
Bye.
Bye.